Uh, Now it is my pleasure to introduce Abdul Gaffar Khan from University of Delhi, who will talk about measure expansivity and specification in pointwise dynamics.
Thank you, Professor, for your kind invitation and introduction. So, my title of the talk, as displays, is measure expansivity and specification in pointwise dynamics. So, the talk will revolve around the possible applications and the importance of the theory of pointwise dynamics that has been started by Reddy in 1970, but in recent years, it has got much more attention because one of the publications that has been published in Dynamical Systems and International Journal and authored by C. Moraz. To express those importance, we will explore the notion of measure expansivity and specification, but from the viewpoint of pointwise dynamics. This work has been published in Bulletin of the Brazilian Mathematical Society and has been jointly written with Pramod Das and Tarun Das during my PhD tenure at the Department of Mathematics of University of Delhi. So before we jump to the theory of pointwise dynamics, let me recall one of the basic notions that laid the foundation of pointwise dynamics, known as expansive homeomorphisms. So this notion was introduced by Woods in 1950, which was published in Proceedings of American Mathematical Society. Basically, a homeomorphism F from a metric space X to itself is said to be expansive if we can find a constant C so that pair of distinct points can be made a constant distance apart, that constant is C, at some instant of integer time. So throughout the talk, we will assume that X is a metric space. And whenever we deal with the measure, we assume that the measure is a Borel probability measure. And we say that map F admits a point X in X, which is expansive, if this constant C varies according to X. So if you choose X, then you will find a distinct constant Cx, so that for every point Y distinct from X, the orbit of X and Y will be Cx distance apart. So this is one of the key motivation that has been raised as a question to Reddy by Gauchang. Before that, let me just give you some basic examples of expansive homeomorphisms. Take a homeomorphism R2R that send X to 2X. This will be an expansive homeomorphism, and the constant C required here is any positive real number. So you can choose any positive real number. Orbit of two distinct points will be C distance apart. One of the important examples is known as shift map, where X is a product of two symbol spaces. Xi, where Xi has two elements at 0 and 1. And the shift map is expansive. This is a shift map. And it is expansive with expansive constant C in 0, 1. For some more examples, one of the other example, one can look into this space 1 and 1 minus n. So the idea is defining homeomorphism is simple. Take 0, 1, 1 upon 2, 2 upon 3, and so on, which is converges to 1, and 1 upon 3, 1 upon 4, and so on. So 0 and 1 define a homeomorphism F in such a way that 0 and 1 are fixed points, and every element is going to the immediate left of its element. This homeomorphism is also expansive, and expansivity constant is 0 less than C less than 1 upon 6. So it is an important question that has been addressed by several authors that can we have a homeomorphism on certain spaces which is expensive. So existential question of expensive homeomorphism has developed many theory of expensive homeomorphism. One such result says that the unit circle and bounded intervals does not admit any expensive homeomorphisms. So in the proof of the result, the notion of periodic points plays a vital role, where a point is said to be periodic if fnx is x for some non-negative integer, for some positive integer n or a natural number n. So there does not exist any expensive homeomorphism as on these spaces, although there are many other spaces that does not admit any such homeomorphism. But these three spaces are important because it has further motivated Reddy to explore the notion of expensive points. So expensive point, as we have recalled, is a point x, so that we can find a constant c depending on the choice of point x, so that the orbit of any two distinct points, only any point distinct from x, that is y is distinct from x, the orbit of y and x can be made cx distance apart. And we say that map or a homeomorphism is pointwise expensive if every point is an expensive point. Clearly from definition, every expensive homeomorphism needs to be pointwise expensive. But the converse is not true even if the phase space X is a compact metric space. This example was given by Reddy itself. Before that, let me just remark that he has proved that even though this is a strictly weaker notion, as he has provided an example which is pointwise expensive but not expensive, the spaces such as x1, the unit circle, and bounded intervals does not admit any pointwise expensive homomorphism. Again, one of the important factors that plays is the notion of periodic points in the proof of this result. The example that proves that pointwise expensive homomorphism need not be expensive is the following that has been provided by Reddy. The idea was that he inserted the shift space embedded the shift space into the unit circle and assume that we can choose a point sequence of points pi, so that none of them are periodic points and their orbit are non-intersecting, that they have disjoint non-periodic orbits. And he further assumed that consider annulus of radius half to 1, this annulus, and inserted a sequence of point rij to satisfy some conditions. Using this, he said that let us embed into a circle that each point has its polar coordinate representation, and with rij, the sequence he has considered, he has assigned pij, with rij considered to be the radius, he has defined the angle in this form. So this element will represent another coordinate, and the collection of all such points is denoted by p. Let's observe that if we take the space, shift space union with this space, and extend the homeomorphism in the most actual way, that pij will goes to pij plus 1. So this homomorphism will be pointwise expensive but not expensive. The constant of expensivity only varies when you choose a point, because if you choose pi, the constant will be 1 minus ri comma 0. And one of the assumption is that ri is converges to 1 as I tending to infinity. So the expensivity constant of CPI approaches to 0. So we cannot find any least such constant c greater than 0, so that every point will have expensive constant c. So the map will not be expensive. Moreover, the space is compact and it's a homomorphism. Again, he has established that even though it's a weaker notion, the space is S1 and the open interval does not admit any pointwise expansive homomorphism. This paper was published in 1970. The Reddy's paper was published in 1970. After that, some attempt had been made in this direction. One can see the notion of sensitive dependence that we have observed. In this paper, Ostrander and York has introduced the notion of sensitive dependence or initial condition in the form of sensitive points. This was in 1980. In 1996, again introduced the notion of chain continuity by using chain continuity points. On one instance, chain continuity point may look like a close version to the notion of shadowable point, but they are actually related to the notion of equicontinuous points, basically the reverse of sensitive points. So he has used this notion to characterize spaces admitting equicontinuous maps and chain continuous maps. So in 2017, Ye and Zhang introduced the notion of entropy points as a pointwise version of entropy. So this is one of the notion that you can say that after expansivity came handy, and it was used by Muthatu to find a sufficient condition for a map having shadowing property to admit a positive entropy. So basically, Ye and Zhang expressed that map has positive entropy if and only if it admits at least one entropy point. So the map has positive entropy if and only if it has at least one entropy. Although Ye and Zhang had studied several other variants of entropy points, but the entropy point was used by Muthatu especially to provide a sufficient condition for a map to have positive entropy. There are some of the paper that has been done in the direction of pointwise dynamics, but important paper that I have put it in the starting that expressed more interest from mathematician was written by Muraz and published in Dynamical System recently in 2016. The paper entitled Scheduled Points. One of the important aspects is that when we combine expansivity with shading, it has several important applications. One of them are decomposition theorem, the other is fault stability theorem, and even still we don't have any proofs in the setting of pointwise dynamics of decomposition theorem, but there are several fault stability theorem in the setting of pointwise dynamics, but we will not discuss that. So before introducing shadowable point, let me recall the notion of shading property, which depends on the notion of delta pseudo orbit and delta tracing. So assuming that F is a homeomorphism, the sequence Xn is said to be a delta pseudo orbit of F if the one-step errors are bounded with a delta distance. That is, distance between Fxn and Xn plus 1 is less than delta. That is, the sequence F will take x minus 1 within a delta wall of x0, and x0 will take F will take x0 to the delta wall of x1. We say that a sequence is said to be delta traced by some point at z if nth orbital time of z is in a delta distance of nth orbital time of the sequence xn. Precisely, if there exists a point z in x0 neighborhood, so that fz will lie in the delta neighborhood of x1 and f inverse z will lie in the delta neighborhood of x minus 1 and so on and so forth. So we say that a sequence xn is through some point x0 if x0 is x. And when we consider a map F to be a continuous map instead of homeomorphism, the indexing of sequences is over n greater than equals to 0. Although the notion will be called delta pseudo orbit delta test, as it will not create any confusion. The map is said to have a homeomorphism is said to have a shading property if for each epsilon we can find a delta positive, so that every delta pseudo orbit of F can be epsilon traced. The examples that we have discussed for expansive homeomorphisms earlier, all of those examples have shadowing property as well. Morales introduced the pointwise version of shadowing property with the name shadowable point, and a point is said to be a shadowable point for a homomorphism F if for each epsilon we can find a delta positive, So that E delta pseudo orbit through X, that is the sequence Xn n belongs to integer and x0 equals to X. So delta pseudo orbit can be of silent traced. Surprisingly, he has observed that if X is compact, then F has shadowing. Allow me to write it POTP as a short key. Has shadowing property if and only if the set of all shadowable points denoted by SFA, this set, is the whole space, provided X is compact and F has shadowing, which is not the case with pointwise expansive homeomorphism, as we have seen the examples. This was one of the key notions that one can see that the notion of shading can be distributed locally and can be studied further. He has concluded his paper with a question that can we have a topologically transitive homeomorphism provided X is compact, so that set of all shadowable points is non-empty and non-compact. So definitely, directly from the global viewpoint, this question cannot be asked. So this has motivated Kawaguchi to further introduce a weaker form of shadowable points, namely quantitative shadowable points, B plus shadowable points, which says that this is not possible. That is, if F is a topologically transitive homeomorphism, then either the map has shading property or the set of all shadowable points is empty. So this is one of the important applications that come out of shading property from the viewpoint of quantized dynamics. Some other application has also been studied, such as I have remarked earlier, like fault stability theorem and sufficient condition for entropy, and as well as chaos later on. In the same paper, Moraz also gave an auxiliary definition. However, he has studied shadowable points for homeomorphism, but he has provided a auxiliary notion that one can define for shadowable points for continuous map, which is something like this: that a point X is a shadowable point if for each epsilon we can find a delta positive, so that E delta pseudo orbit of F through X can be epsilon traced through F. So here the sequence delta pseudo orbit means the indexing is n greater than equals to 0. In the main result of this talk, we always assume that F is a non-invertible map whenever we are dealing with a shadowable point. So F is always, in fact, F is a continuous map. So the first question arises that, can we say that if F has shadowing, then set of all shadowable points is again X? So we establish that this is true, provided this map is surjective. That is precisely if F is a continuous surjective map of a compact metric space, then F has shading if and only if every point is a shadowable point. Surjectivity, although is not required, but our other results will involve surjectivity. So we have normalized it in the hypothesis itself. Although one can observe that surjectivity is not required in the proofs. And in fact, the proof has been later on further simplified by Arbiter and Trico. So let me just give you a proof of this fact. Definitely, if F has shading property, then the set of all shadowable point is nothing but the whole space X, as for every epsilon greater than 0, we can find a delta, which will work for every point of the space. So the converse is not the forward implication is not a difficulty. So prove the converse, we assume that the set of all shadowable points is X, and contrary, F does not have the shading property. So to prove this with a contradiction method, assume that for an epsilon positive, we can choose such an epsilon, so that for this epsilon, we can find a sequence of 1 upon I pseudo orbits, I varying over natural number, so that these pseudo orbits denoted by yi cannot be 2 epsilon trace, as this cannot be 2 epsilon traced. So Now yi's are sequence is x and I. So we fix a sequence of initial coordinates x01, x02, and x03, and so on and so forth. And using the compactness, we can assume that this sequence will converge to some point z as I tending to infinity. Now z is a point of x, and set of all schedulable points is nothing but the whole space x. So it says z must be a schedulable point. And so for this epsilon we have chosen, we can find a delta so that every delta pseudo orbit through the point z can be epsilon traced. So we will use this to arrive at the contradiction by in the following way. First, we have considered a new delta pseudo orbits that are passing through z, and the use of the delta 1 upon I pseudo orbits yi is given in the following way. We define a new sequence x and I bar, also denoted by yi bar, so that if n is not equals to 0, then the elements are x and I as in yi, and if n equals to 0, we have replaced the initial coordinate with z. So this will form a delta pseudo orbit to the point z, because it can be following the, it can be done in a similar manner, like yi bar will be useful. Yi will be useful to prove that this also form a delta pseudo orbit. So if n is not equals to 1, we have to basically show that distance between yi fi yi bar and yi plus 1 bar is less than delta, to show that yi bar from the delta pseudo orbit. So in particular, we can write yi with x's, and just reduce into the following cases. If n is not equals to 1 and n equals to 1, so distance between xn minus 1 I bar and xn I bar is same as this, because we have assumed that if n is not equals to 0, then xn I bar is nothing but xn I. Only the initial coordinate has been replaced with z. So since this is a delta pseudo orbit, we have already assumed that this forms a 1 upon I delta pseudo orbit. Right? We have assumed that yi is a delta pseudo orbit, so this will be a distance less than 1 upon I, definitely, because this forms a 1 upon I pseudo orbit, and the problem will occur when n equals to 1, and at n equals to 1, n minus 1 I will be x0 I bar, which is z. So this is nothing but distance between fz and x1 I, and applying on the triangle inequality with we can assume that this is less than equals to the following quantity. Now fx is compact and f is uniformly continuous, and we have already assumed that x0 is approaches to z, so we can choose a small enough natural number j, so that distance between z x0j will be less than delta by 2, and this j will also imply that distance between fz and f0j will also less than delta by 2, where z, sorry, as so distance between z x0j is small enough to 1 upon j will imply distance between. So the uniform quantity will come handy here, and we can further assume that 1 upon j is also less than delta by 2 without association. So in particular, this quantity can be made to be less than delta upon 2 plus delta upon 2, which is delta. So this sequence will form a delta pseudo orbit. Now this delta pseudo orbit is passing through the point z, and hence this will be traced by some point, say zj, distance, that is distance between fn zj and xn j bar will be less than epsilon for all n greater than equals to 0. In particular, for n greater than equals to 1, we will assume that xn, we can see that it is xnj less than epsilon. So to arrive at the contradiction, we will see that yj can be 2 of silent traced. But we have already assumed that none of the yi delta pseudo orbit can be 2 of silent trace. So we will get a contradiction, and that can be 2 of silent trace with the same point zj that we have obtained by shadowing of z on the delta pseudo orbit yi bar yj. So for n greater than equals to 1, we have already observed that this is less than 2 of silent. For n equals to 0, we again apply triangle inequality. N equals to 0 will reduce it to 0, that is same as this, and applying triangle inequality with zj, and this quantity is less than of silent. As from the previous, we have observed that distance between f and zj and x and j bar is less than x, and 0 bar is nothing but z. So this is less than epsilon, and by assumption that it is less than less than delta by 2, which is less than epsilon, we observe that this is less than 2 epsilon, and hence distance between f and zj and x and j is less than epsilon, which implies yj can be 2 epsilon, which is a contradiction. So for the given epsilon, we can find some delta so that it can be delta traced, and it will work for every x. So this will prove that if shadowable points of fx is x, this f must have shading property. This previous result was to establish that can we say the similar case in continuous map, but the more important result we discuss now. To discuss those results, we need to define some notion. First notion is known as topologically transitive points. Here, the topologically transitive point, we mean this point x is topologically transitive if for every pair of open set u and v where x is in u, the orbit of u and v will intersect. Some author also say that map point is transitive, it has a dense orbit. This is different from that point, and we can observe that if the point is topologically transitive, then it may not have a dense orbit. So we say that a point is transitive, this happens. So for it is easy to observe that f is topologically transitive. By topologically transitive, we mean that whatever open set you choose, u and v non-empty, the orbit of u and v intersect at some positive integer time n. So here the dependency on x does not vary. It is easy to observe that f is topologically transitive if the set of all topologically transitive points is x. This follows from the definition. Really. Moreover, the set of all topologically transitive points is closed. Similarly, we can introduce topologically mixing point, that is the orbit of any two non-empty open sets u and v where x is in u will intersect except for finitely many times. And similarly, we can observe that f is topologically mixing where map set is said to be topologically mixing if for every pair of open set u and v will intersect except for finitely many times. And that is the definite does not depend on the choice of point x, and it is topologically mixing if and only if the set of all topologically mixing point is x. Again, topologically mixing point set of all topologically mixing points, that is x is closed. These sets are also invariant under homeomorphism, so conjugacy. So f is conjugate to g, then we can say that topologically mixing points can be transferred within the conjugacy. But these set need not be open in general, that is set of all topologically transitive points, set of topologically mixing points need not be open in general, and topologically mixing point is topologically transitive, but the converse need not be true. Here one can find easily many examples. Next notion is, we call it has dense set of periodic point, but it is just a redefinition of the point of saying that the point is a limit point of the set of all periodic points. So we just defined it in this way because it is much more giving sense to the notion of Devaney chaos that we will see here. Again, the notion of Devaney chaos was introduced in 1980s, late 1980s, and it says that the map is said to be Devaney chaotic if F is topologically transitive, the set of all periodic points is dense in the space X, and it has sensitive dependence of initial condition. Basically, a map is said to be sensitive dependence on initial condition, or sensitive if there exists a constant delta such that if X in X, then we can find a sequence Xn converges to X and a sequence of non-negative integers such that distance between is greater than that. So it was observed by Banks and all in 1992 that sensitivity is redundant. That is, provided the map is topologically transitive and has dense set of periodic points, then the map must have sensitive dependence on initial conditions. This has motivated us to introduce this notion from the viewpoint of pointwise dynamics, and we have introduced the notion of Devaney chaotic point. And the point is said to be Devaney chaotic if it is a topologically transitive point that we have defined earlier in that sense, and it has a dense set of periodic points around its neighborhood, or it is a limit point, and it is a sensitive point as well. So the set of all the Devaney chaotic point is denoted by this set. One can easily observe that pointwise Devaney chaotic map is also Devaney chaotic. So this is an equivalent condition. The idea is using the result that has been proved by Banks and all that we have quoted in the last slide, that is here. So definitely Devaney chaos will imply every point is Devaney chaotic, and converse follows from the fact that F is topologically transitive if and only if every point is a topologically transitive point, and since we are obviously assuming that space is a perfect metric space as we are working on sensitivity. So we assume that space is a perfect metric space. So map has dense set of periodic points if and only if every point is the limit point of periodic point. So these are two equivalent conditions. So if you observe that using these two equivalent conditions, we can simply conclude that pointwise Devaney chaotic map are Devaney chaotic and vice versa. In 1971, Bowen has studied the notion of specification points to study the distribution of periodic point in the phase space, and it has been later connected with the notion of Devaney chaos and entropy. This result has motivated us to study the connection between specification property from the viewpoint of pointwise dynamics and related to the notion of Devaney chaos, and we will further relate it with the notion of entropy. That one of the two of the main motives of this paper. So let me just recall the notion of specification point that we define. We say that a continuous map F, for a continuous map F, X is a specification point if for each epsilon we can find a time gap such that for each k in n, take any finite sequence of elements of X and finite sequence of integers, non-negative integers, so that the time gap between A2 and B1 is at least m. Then these orbits can be piecewise traced within a epsilon distance by some point. So the set of all such points will be denoted by the following set, and we say that a map has pointwise specification property if every point is a specification point. If this time gap m does not depend on the choice of point X. That is, for every epsilon, we can find a time gap M which will work for every X, then the map is said to have a specification property. If we can choose such a tracing point that traces the pieces of these orbits of the sequence x1, x2, xk, the pieces means the piece a1, b1, a2, b2, and ak, bk, the following way. Can be traced by a periodic point, and the point is said to be a periodic specification point. And again, if this epsilon, for epsilon, we can choose a m which does not depend on the choice of point x, and then the property is said to be periodic specification property in the current literature. And again, we say that a map has pointwise periodic specification properties. Every point is a periodic specification point. We established that if F is a continuous surjective map of a perfect metric space and F has pointwise periodic specification property, then it must be Devaney chaotic. So it is enough to put that it is pointwise in a Devaney chaotic. It was established in 1974 by Sigmund that this is true provided the map has periodic specification property. So the proof is divided into two parts. The first says that every specification point must be a topologically mixing point. And moreover, if every periodic specification point must have dense set of periodic points in its neighborhood. So it is one can see that so this map is Devaney chaotic, but it does not have pointwise periodic specification property because it does not have topologically mixing property. And from lemma 2.1, we can see that if the map have pointwise periodic specification property, then it is topologically mixed. So the converse of this theorem is not true. Also, similarly, we can observe that topologically mixing point need not be a specification point. So to look at, just take the homeomorphism x square. So the point 1 x equals to 1 will be a topologically mixing point, but it cannot be a specification point because we can choose small enough of silence so that once the orbit leaves the silent neighborhood of 1, it will never come back to the neighborhood of x equals to 1. But as we have defined that this must be true for every finite sequence, the finite pieces of traces can be possible, and so there must admit at least one point which always comes back to its silent neighborhood after leaving it. So this is not possible. So this point is a specification point, but this is not a specification. This is a mixing point, but it's not a specification point. Again, the example that we have seen earlier, that 0, 1 upon n, 1 upon n, that can be, that space with the identity map will give that it has a dense set of periodic point, but it's not a periodic specification point, one which will establish that the converse of lemma 2.2 is also not true. So to prove the theorem 2, we will first establish that pointwise periodic specification implies every point is a topologically mixing point, which is equivalent to say that the map has topologically mixing property. And then we will establish that it has dense set of periodic points, and it pointwise periodic specification implies every point has dense set of periodic points. So it has a pointwise Devaney chaotic property, and we have seen that it must be Devaney chaotic. So the lemma 2.1 can be used, is based on the definitions basically. So suppose that x is a specification point, and it is a, we need to establish that it is a topologically mixing point. So choose a pair of non-empty open set uv of x, where x is in U, So we can choose a small enough epsilon so that ball centered at x of radius of epsilon is contained in U and centered at y of radius of epsilon is contained in V. And by the notion of specification point, we can find a time gap m by the specification property of x. So we will see that FNU intersection V is non-empty for all n greater than equals to m, where m is due to the specification property. Just to see that, we fix an integer n and we will find some point in U so that Fn that of that point will be in V. So to do that, we fix a sequence where x1 is x because it is through x. Specification void the sequence x1, x2, x3 must be through x, and we further fix a point x2 which is in f minus ny. We are assuming that it is surjective, so this is possible. And we are further fix a sequence a1 b1 equals to 0 and a2 equals to n equals to b2. So a2 minus b1 is greater than equals to m. So by specification property, we can find a point Zn depending on this sequence, which will piecewise trace this orbit. Piecewise trace basically here is implying that xzn and x1 is less than epsilon, and distance between fn and zn, fn zn and x2, fn zn and y is less than epsilon because fn x2 will be y. So we found the point zn, which is this ball and its orbit is so FNU intersection V is non-empty, and since n is 2 then arbitrary, we get the required density property. To say that every periodic specification point has a 10 set of periodic points, we first observe that if the point is a periodic specification point, then it cannot be an isolated point, which is a bit trivial, but let me just give you the overview. So suppose that x is a isolated point and either it is a periodic point or it is not a periodic point. So if it is a periodic point, then with prime period n, then the orbit of x with its complement is empty for fk orbit, as fk and x is nothing but x. So this set is open, this is open, and we have seen in lemma 2.1 that the point which is a periodic specification point must be a topologically mixing point, because every periodic specification point is a specification point and every specification point is a mixing point. So we have given two open set U and V, said that F and U intersection V is non-empty for finitely many. So this is not possible. So this can't be a topologically mixing point. So this can't be a periodic point. Similarly, if it is not a periodic point, then we can see that F and X intersection X is empty. So again, we have observed two show the existence of two open set U and V, so that the orbit of U and V does not intersect except for finitely many times. So again, using the lemma 2.1. So now we suppose that use an open set containing X. So suppose that X is not a periodic point, because we have observed in the previous case that X is a periodic point and X is not a, so it is not an isolated point has been established. So further we assume that suppose that use an open set which contain X, and suppose that X is not a periodic point of F. X is not an isolated point has been established. Now we are further assuming that X is not a periodic point, and we'll consider the case where X is maybe a periodic point to establish that X can be seen as a limit of sequence of periodic points. So suppose that X is not a periodic point. So for epsilon, we can find a ball which is contained in U. And since X is not an isolated point, this set will have a non-empty, this set will be non-empty. So for this epsilon, we can choose M by the definition of periodic specification point, and again fixing a sequence in the following way. The initial coordinate x1, because the sequence must be through x to apply the definition of periodic specification, and x2 is some element of x, can be any element, and fixing the sequence a1 equals to 0, b1 equals to 0, a2m and b2m. Then applying definition of periodic specification property of x, we can find a point, periodic point because of periodic specification property, which will trace the pieces of this orbit. So this is again nothing but imply that distance between z and x1 is less than epsilon, and distance between fz and fx1 is less than epsilon. So we don't need this. We just need to show the existence of the periodic point z in the epsilon neighborhood. Since x is not a periodic point, so z cannot be x. So the diluted neighborhood contains a periodic point and it can be seen as a periodic point. So we now suppose x is a periodic point. In that case, we proceed as follows. Suppose that x is a periodic point with prime period m, and choose a p and natural number p, so that the quantity q is less than the diameter x by 4. So here this quantity is distance between fjx and fkx, where j is not equals to k. Okay. So j is not equals to k here, and definitely m is not equals to 0. So this quantity will be a non-negative number as the prime period of x is m, and we choose a natural number p so that this q is less than diameter of x by 4, where diameter of x is the diameter of the complementary space, and diameter of the space x. So since f is surjective, we get that fn is surjective, and hence for q small enough, for epsilon smaller than q, we will use the definition of periodic specification property, and this will give the existence of the integer m. Now note that for every epsilon small enough less than q, we can choose a point y, so that the orbital distance between f and y and orbit of x will be at least epsilon distance, because q is less than diameter of x by 4, so the existence of y will follow for every natural number n, and fn is surjective. So using this observation for epsilon, we can find out integer m by periodic specification property. Again, fixing the sequence in this form, x equals to x1 and x is some element of x. But this case will require that x2 is chosen, so that the distance between fm and x2 and orbit of x is greater than epsilon, and this exists because of the following observation. So x2 is chosen in this form. So for the fix the sequence a1 equals to 0 equals to b1 and a2 equals to b2 equals to m. You can find a tracing point, periodic point z, which epsilon trace these finite pieces of orbits. So observe that because of the distance is greater than epsilon, we must have z not equals to x. Otherwise, the distance between fm x2 and orbit of x will be less than epsilon, and hence z can be chosen to be a point in the diluted neighborhood. And even epsilon chosen orbit, we get that it is a limit point of the set of all periodic points. So which completes the proof, as we have considered the cases where x is either a periodic point or not periodic point. We have further observed that, which has been proved by Banks and all, that the notion of sensitivity is redundant in the notion of Devaney chaos. We observe that notion of sensitive point is also redundant in the notion of Devaney chaotic point. That is, if x is a topologically transitive point and has 10 set of periodic point at x, then it must be a sensitive point. To see that, first observe that, assume that x is a topologically transitive point which has 10 set of periodic points in its neighborhood. We claim that x is a sensitive point. Now, since f has 10 set of periodic point x, we can choose a delta positive, so that distance between x and orbit q is greater than or equals to 2. In fact, there exists a periodic point we can choose which has suppose period m, so we can choose the minimum of the distance between x and f phi. Phi is varying from m0. So q is not equals to x, so we can assume that this is possible, and using this fact we will find such a positive delta. So that distance between x and orbit of q is finite being a periodic point, is written as delta by 2, and we fix eta equals to delta by 8 and observe that 4 eta is this one, and eta will serve as a sensitivity constant of f at x, which is required. The sensitive point which was introduced by our standard log, as we have quoted earlier. So to establish that, we need to find a point y given an open set O containing O. We need to find a point z in O, and then n greater than 0, so the distance between f and x and f and z is greater than eta. So to prove this, suppose that O is an open set containing x and choose a periodic point P of f. Suppose that it has a prime period n. Because it has a dense set of periodic points, we can choose a point P distinct from Q definitely within a set deleted neighborhood of x, where denoted by O prime minus x, where O prime is the intersection of O and ball center x of radius eta. So we set W to be this set, and this set is non-empty because this will contain Q and it will be open, being F is a continuous map. Now, by the topological transitivity of x, we will find the point, say y, and by using the denseness of periodic point, we will find a point z. Both, we will observe that one of this point will satisfy our need, that distance between fn of x and fn of some fn is not the period of t here, will have a distance greater than eta. So first we will find the point y using topological transitivity. So since S is a topological transitivity and O dash is open, so we can find a point y in this neighborhood and a k natural number, so that fky will belongs to W, because fn O prime intersection with W is non-empty, so the point y will exist, and let j be the integer part of k upon n plus 1. So being an integer part, this quantity will satisfy, that is 0 less than equals to nj minus k less than equals to n. So we get that simple calculation will imply, computation will imply that fnjy can be written as this, which further can be written as this, but fky belongs to W, so this set will belongs to W, but W is the intersection of f minus I of fi all fiq centered at eta. So this set will nothing but contained in this ball, that is centered at fnj minus q and of radius q, radius eta. So again, applying triangular inequality on the set, we will observe that this will occur. Triangular inequality is applied using point P and fnjy. We have inserted this point. So observe that, we further observe that distance between fnj py fnjy is nothing but this, because P has a period n. So fnjp is nothing but P. Now using this equation, that is 1, so taking every element on the left hand side, we will get that distance between P fnjy is greater than or equals to distance between x minus distance between x and P, and minus this. So observing that P is in deleted neighborhood of x, fnjy is in this neighborhood, and distance between x and orbit we get in. Observing all these, we can see that 2 eta can be written as in this form, that is less than distance between x and fnj minus kq, because fnjy is in the center at fnj minus kq and eta, so this will minus 4 it, sorry, this follows from the following observation, and this will follows from the fact that distance between xp is less than eta, so this will hold. Similarly, this quantity will come because of this fact. So this is nothing but this, as we have seen in the last quality here, this one. So applying triangle inequality with respect to f and jx. So we have observed that distance between f and jx, j is fixed, n is fixed, and the distance between f and jx, y is greater than 2 eta. So either this quantity must be greater than eta, or either this quantity is greater than eta. So this point was existing due to the density of periodic points in the neighborhood of x, and this point y was existing due to the transitivity. So since O is chosen arbitrary, we get that x must be a sensitive point with respect to eta. So again, we establish that sensitivity is redundant in the definition of Devaney chaotic point, and one can observe there's well-known example. Using those examples, we can see that if we drop one, then the other will not go. That is, transitivity will not individually imply sensitivity of a point, and density of periodic point will not individually imply sensitivity of a point. The third application that we have observed that if f is a topologically mixing point, then every shadable point is a specification. But this is important because we have not remarked till that pointwise specification is equivalent to specification or not. Such as in mixing, transitive points and shadable points. We have observed this is true, but we have in the search of this answer of this question, we have observed that if the map has shading property, then this is true. Whether it is true individually or not, we are not aware. So suppose that f is a topologically mixing point, then every shadable point is a specification point. We will use this result to establish our claim. So the proof is based on the definition more or less. So suppose that x is a specification point of f, and initially we will use a notion of topologically mixing extensively. So for showing that x is a specification point, choose an epsilon. For epsilon upon 2, we can choose a delta by the shadowing of f through x, because x is assumed to be a shadable point. Now we have further assumed that x is a totally bounded metric space in this condition, in this theorem. So x is totally bounded, so we can choose a finite subset which said that the following wall center at Zi of radius delta by 2 will form a open curve for x. Now since f is topologically mixing, so f and u intersection v is non-empty for every pair of non-empty open sets except for finitely many times. So fixing u and v to be these sets, we can choose the maximum of all those m's and denoted by mij's. And so we can observe that f and u and v will intersect for all n greater than equals to mij, where u and v are element of this curve. So if we define m to be the maximum of this, so we will see that this maximum will help us to establish that time gap required corresponding of epsilon for the specification property of x. So choose a finite sequence starting through x of elements of x and a sequence of integers, so that time gap is greater than or equals to m plus 1. M is the integer that we observe. We assume that the time gap required is m plus, we claim this, that is time gap will be m plus 1. So for each z, this is a simple notation that bz will denote the set of the open curve which contains z. So if z is in ball z1 or comma delta by 2, then bz will denote ball z1 centered at z1 of radius delta by 2. So now we will use f and u intersection v is non-empty for all n greater than equals to mij to construct a delta pseudo orbit wi. So it is constructed in the following way: since aj minus bj minus 1 plus 1 is greater than equals to m, using this equality, we can find a point in the balls and containing fbj plus 1 xj, so that the orbit of f aj minus bj minus 1 plus 1, which is this set, is greater than equals to m. So by mixing, we can find a point yj which will intersect the ball containing faj plus 1 xj plus 1. So it will help us to define a delta pseudo orbit in the following way wi. So observe that 0 less than equals to a1, we are assuming x, and for aj to bj, the element fi xj are nothing but the piecewise orbits we need to trace, piecewise orbit that we need to trace. So if we can see, if we can prove that this can be traced, this delta pseudo orbit can be of silent rays, then these pieces can be of silent rays without intervally. So that was the idea, to consider delta pseudo orbit and then applying the notion of shading property SHFX, where X is assumed to be a shadowable point, and conclude the result. So using some simple calculation, we can observe that this will form a delta pseudo orbit. This will form a delta pseudo orbit, and hence it is starting at n equals to 0. W0 is nothing but X. So this forms a delta pseudo orbit through X, and we assume that every delta pseudo orbit through X can be of silent by true traced. And assuming it to be of silent by true trace, we can silent trace. So in particular, the pieces that I have just remarked here, this one corresponding to this can be a silent trace, and hence every piece can be a silent trace. And since K was chosen arbitrarily, we can observe that the point is a specification point. So using above theorem, we can conclude that if F is a uniformly continuous surjective map of a totally bounded metric space, then F has pointwise specification if and only if it has specification property, provided F has shading property. We still don't know that whether this relation holds in general or not. To prove this fact, definitely specification will imply pointwise specification. To prove the converse fact, we have used the result to say that if F has shadowing, then F has topologically mixing and F has specification. Under the same assumption, these two notions are equivalent. This has been proved by Pramodas and Tarundas in the paper Formulation General of Dynamical and Control System. So we have used this observation and applied it to the topologically mixing to establish that if it has a pointwise specification property, then every point is a mixing point and it has topologically mixing. So the map will have shading property as well as topologically mixing. But this is equivalent to say that it has a specification property. So in the presence of shading property, these two notions are equivalent. The other application of specification point is following. To say that if F is a uniformly continuous surjective map and has at least two distinct specification points, then it has positive entropy. So it is well known that if it has specification property, implies that entropy of F is positive. We have established that instead of specification property, the existence of two distinct specification points are more than enough to guarantee this fact that the map will have positive entropy. As it is known that if the map has specification, every point is a specification point, so we just that only two distinct specification points are more than enough. Where the notion of entropy is defined like this is due to Bowen. To this fact, suppose that X and Y are two distinct specification points, and for this choose a silence so that idea is to find sufficiently many distinct points so that the lower bound of the entropy can be calculated and turned out to be at least positive. So for this epsilon, we can choose a positive integer m, which will work for the specification property of X as well as for Y. So that is for every finite pieces of orbits, a sequence finite pieces of orbits start through X or Y can be epsilon traced. But the time gap is at least m. So now consider two n plus 1 distinct tuples z0, z1, z2, zn and a z01, z1, z2, zn prime. So we will observe that if these elements z0, zi's and zi primes are in X and Y, only X and Y, then we can find a tracing point for the sequence will be distinct. So for this sequence is nothing but a0 is 0, these are multiples of m. So a1 is b1 is m and so on and so forth. So we will observe that if the tracing points are not same, then this will hold because of the orbits are tracing in piecewise orbits. So the distance between xi is less than 2 epsilon, which is again a contradiction. Similarly, we will observe that if suppose that z0 is z0 prime. So this equality will is justified using the observation that z0 is not z0 prime. But if this will happen, we will simply extend the sequence z0, z1, z2, zn by adding another element zn plus 1, and similarly this sequence by adding element zn plus 1 prime, where these zn plus 1, zn plus prime satisfy the following assumptions. So these are the inverse orbit of an inverse image of n plus 1 m at x. So again, we can use and this fact that it can be a silent trace, and using that if zn plus 1 belongs to this set, we will observe that z and z prime, the tracing point must be distinct, because if z equals to z prime, again using the time equality, we will observe that distance between x is less than 2 epsilon, which is a contradiction. And for since we have observed that z0, z1, zn are, if we take 2 to the power n plus 1 distinct couples because these belongs to x and y, we can choose 2 to the power n plus 1 distinct tracing points. So we further observe that whatever the tracing points we have obtained using these sequences can be n plus 1 m of silence separate. Again, to establish that, we will use a contradiction method that if they are not separated, then again the distance between xi will be less than 3 epsilon, which is contradiction to our assumption. So simply applying to the entropy, the definition of entropy, we will observe that the quantity will be at least 1 upon n plus 1 m log 2 n plus, because we have at least 2 to the power n plus 1 m silent separated set, which is log 2 by m, which is greater than 0. And it will observe that, and hence f has positive entropy. Yeah. We can see that f can have positive entropy provided it has no distinct specification points. Just look at this example. It has been proved by Das and Das that this map will have positive entropy. But using the similar arguments as we have used, that x square, this map x square has no specification point, can be used to establish that it has even no specification points, but it has positive entropy. So the converse of this result is still not true. So combining the above results, we can show that if f is topologically mixing and has at least 2 distinct shadable points, then the map has positive entropy. Now we will come back to the notion of pointwise expansivity, but in the sense of expansive measures. So we can observe that f is expansive. That was introduced by Woods if and only if there exists a constant c greater than 0, such that gamma delta x denoted by y this set is nothing but the singleton x. So this observation has motivated Bowen and Servant to study the notion of expansive measures. So basically, a Borer priority measures we are assuming from whenever we are talking about measures. So, but they have defined it for in general. So a measure is said to be expansive if the measure of this set is 0. The measure of gamma delta x is 0 for some the constant delta. The such constant delta is said to be a constant of expansivity for measure mu. So this has motivated us to combining the notion of pointwise expansivity with measures to introduce a notion of pointwise expansive measures. And we will see that many results that has been proved by point for expansive measure and pointwise expansive homomorphism can be seen from the viewpoint of pointwise dynamics also. So the notion is said to be pointwise expansive measure. Measure is said to be pointwise expansive measure. For each x, we can find the point cx. So the measure of this set is 0. So the constant of expansivity, as in the case of expansive homeomorphism, and pointwise expansive homeomorphism, here also the constant will depend on the choice of point. So we say that f is pointwise expansive bi-measurable map. We can define it for bi-measurable maps. If this is true for every non-atomic Bowen priority measurement. So the constant Cx will work for expansivity for every non-atomic Bowen priority measurement. So the pointwise expansive measures, as we have recalled, can be defined in the following way. So firstly, we have observed that if f is a bi-measurable map of a separable metric space, then the set of points having converging semi-orbits must have measure 0 with respect to any pointwise expansive regular measure. So the key ingredient to establish this result is Lewson's theorem. So basically, we have established that the set of all points having converging semi-orbits must be 0. Improve the following results, which can be stated in the following: the set of points having converging semi-orbits and the expansive homeomorphism is countable. So if you take f to be an expansive homeomorphism, AFX is countable, and it is also proved by Morales and Servant that if the space is separable metric space, then and the measure expansive, then AFX has measure 0. So to do this, we have divided the proof in 2 steps. So first lemma says that if f is a bi-measurable map, then we can find a sequence xi which is contained in this set. This set is coming. This sequence is coming due to the separability of the metric space. The set is basically defined like this, that it contains all elements z in x, and the set x depending on x, y, n, and m natural numbers, so that distance between f minus izx and fizy are less than 1 upon n, because we are assuming that f is a bi-measurable map, so f minus i is built-in. So proof is falling from the theoretical containment. So we can take one element in AFX, and we can simply say that the sequence xi, which coming due to the separability, we can replace the sequence xi here and observe that if z is in AFX and z is in this sequence, simple observing that the fact it has converging semi-orbits will come in handy, and it will follow from triangle inequalities to follow that z must be the element of this set, and hence AFX will satisfy this. So we have further observed that if mu is a Bowen measure and each measurable Lindow subset K with measure of K greater than 0 will satisfy this property. That is, we can find the points Z in K and delta node, so that measure of K intersection of this set will be positive. The proof based on contradiction matter, if this is not true, then we can find a sequence which admits a countable subcover, and K can be written in that union of that set, and each set will have measure 0, which will imply the measure of K will be 0, which will be a contradiction. So finally, to prove this, we will use our two lemmas in the following way. Suppose that mu is a pointwise expansive measure. So for each a in AFX, we choose the expansivity constant CA, so that measure of gamma FCA is 0. So we are assuming that mu is a pointwise expansive measure. So for every point, we can have a expansive constant CA, and CA greater than equals to 1 can greater than equals to 1. So we can divide the spaces of point in the following way, that it is the one set contains the set of all points which has expansivity constant greater than equals to 1. Other set will contain greater than set of all points which contains expansivity constant greater than equals to 1 upon 2, and so on and so forth. So we will do this procedure here basically. So AFX is, for each A, we fix the constant C and we define a set A, so that measure of A is greater than 0. So for each n, we denote the set A to be the set of all points, as we have in the following way. So from lemma 6.1, AFX will contain in this set. So in particular, AM will contain in this set, where M is a natural number which corresponds to the set A, a subset of A, that the measure of AM is greater. The set exists because assuming that measure of AFX is non-negative, we can find a subset A in AFX, which is divided into this set, which is a decreasing sequence, definitely. So it can be written in this form. So we can find a M so that it has positive measure. So because we are using a contradiction method, so we are assuming that AFX has positive measure. So this set AM will have positive measure, and AM is contained in this set because of lemma 6.1 that so this set will imply that AM is contained in intersection of over union. So AM will contain in the union for each n in n because it is contained in the intersection over. So basically it will contain in each of this set for every n. So for each n we can fix a triplet k prime m so that measure of one of the set is greater than 0. If measure of each set is 0, so measure of AM will be 0. So this will be a contradiction to this fact. So we assume that we can choose a triplet kk prime m for each n depending on such a measure is positive. So in particular, for this capital M here, and we replace this capital M, we fix a triplet kk prime m and assume that it has a measure 0 and set it to be the set B. So now using the Lucian's theorem, we can say that we can have a measurable subset C of psilon. So that measure of x minus C of psilon is less than of psilon. We are assuming that polar probability measures are we are working on. So we can do this. So measure of x minus C of psilon is less than of psilon, so that it is Fn restricted over C of psilon is continuous. We can repeatedly apply this theorem to find such a C of psilon. And this is true for minus m less than equals to n. So in particular for epsilon equals to measure of b by 2, we choose a measurable subset C in the following way so that Fn district over C is continuous. That is applying Lucian's theorem for epsilon equals to measure b by 2. So and again, since this set is Lindelof, B intersection C is Lindelof, we can apply lemma 6.2 to show the existence of a point Z in this set and delta not positive, so that measure of this set is positive. Now, since Z is in C and Fn restricted over C is continuous, we can find a delta due to the continuity of Fn at Z such that distance between ZW less than equals to delta will imply that this distance is less than equals to CZ, the constant of expansivity. So now this set, using this continuity and the definition of AM, we will observe that this set is a subset of gamma CZZ. That is due to the that is the definition we have defined gamma delta x. Y belongs to x, so that distance between f and x and f and y is less than delta. So this set is contained in this set by using the continuity and definition of AM. We can observe that. But this set has measure 0. This set has measure 0 because Z is expansive. The constant of expansivity for Z is CZ. So this set will have measure 0. But with our assumption, due to the lemma 6.2 that we have chosen Z in such a way that this set must have positive measure, so we arrive at a contradiction. So the assumption that measure of AFX is positive is incorrect. So using the similar arguments, we can further establish that if the set of if F is bi-measurable map of a separable metric space and measure is pointwise expansive regular, then the set of all points positively asymptotic to P and negatively asymptotic to Q will also have measure 0. This which will improve the fact we say that if F is a pointwise expansive homomorphism of a compact metric space, then the set of points positively asymptotic to Q and negatively asymptotic to Q is at most countable. So this was proved by Reddy itself that this set is at most countable. We have established that if measure pointwise expansive measure, then this set has in fact measure 0. Proof runs on a similar line of proof of theorem 6. So this proof of theorem 7 runs on the similar line. So you observe that the set of all periodic points that we have studied is at the most countable, which we have quoted earlier, provided it's at the most countable, provided f is a pointwise measure, f is pointwise f is a pointwise measure expansive. Uniform equivalence. That is, f and f inverse are uniform equivalence and x is compact. So we can observe that this is also x is compact. So if periodic point is at most countable, we have further observed that using the above result, we can also establish that periodic point is at most countable provided f is a pointwise measure expansive map, which is a uniform equivalence and x is compact. In fact, this will be true for completely separable metric spaces. Recently, we have further observed that we have obtained further applications related to an expansivity and stable classes for pointwise measure expansive. But I will just give the current work that is happening. Recently, Arbiter and Rigo introduced uniformly expansive points. So this is important because pointwise expansive homomorphism need not be expansive, but it has been observed that if x is compact, then f is expansive if and only if every point is a uniformly expansive point. So this is one of the important notion that has been introduced by Arbiter, and it has been further observed that uniformly expansive point can also be used to provide the sufficient condition for the entropy of a system, provide the map point is a shadable, non-metric, non-isolated, non-periodic. So several application can be used, can be obtained in the using the theory of pointwise dynamics. We have also in recent work we have also worked on uniformly expansive points for measures and used it to obtain stability theorem in the setting of pointwise dynamics for measures. So that's it for today. Thank you.
Let us thank Abdul Gaffar. Any questions, comments?
Kostya has a question. Oh, no, this is no.
I had a small question about the entropy estimate. So if you have just two specification points, you have estimate something like log 2 divided by m when m is this constant from the definition. If you have more specification points, can you improve this, obtain a better estimate?
Maybe, I'm not sure. We haven't thought about that.
Okay,
maybe we can do that.
There's no reason.
I think it is possible.
Okay.
We have for shift, we have plenty of every point is specification points. No? And entropy doesn't grow because of this.
Yeah, that's true.
I have a question. What about, say, piecewise continuous maps of interval? Because part of your theory was about continuous maps. So that's...
Will you please repeat your question?
Question is that part of your theory was about continuous maps.
Right.
What about piecewise continuous maps of interval, let's say?
It is true for any continuous map.
Pardon?
The theorems hold for any continuous maps.
Continuous
maps are not continuous.
But for piecewise continuous,
finitely many discontinuity points.
yeah, which would include
Okay.
beta transformations.
I am not aware. I think I have to think.
Any other questions or comments? Okay, since we don't have more questions and comments, let us thank Abdul Gaffar again then.
Thank you very much.
Thanks.
Thank you.
Thank you so much.
Goodbye.
Bye-bye, everyone.
Bye. Good night.
Bye. Oh, Michał appeared.